Okay. Today we have the great pleasure to welcome Professor Michalis Vassiliou, who is an assistant professor in ETH Zurich. He holds a chair in seismic design, and he's an expert on seismic and mechanical metamaterials. And I believe this is what he's going to talk today in conjunction with 3D printing facilities. So Professor Vassiliou, if you may.
Thanks a lot, and thanks a lot for the invitation. There is not a lot about metamaterials. It's just, you know, you can call it a metamaterial what I'm doing, but I think it's, you know, it's just notches and circuits for me. So anyways, let me start sharing. No, I need to start sharing. So Zoom, share screen. I'll be sharing this one. And this one I need to minimize. That goes here. So again, hello, and thanks a lot for inviting me. Today I'm gonna be talking about some applications of 3D printing in seismic testing of structures. First of all, we need to understand why we need to tilt multiple specimens on a shake table. And this is the reason why we need small scale testing. And the second part of the lecture discusses how we can use 3D printing to help us do so. So let's start with what the state of the art in seismic model. Oops, sorry, this should not have been here. What happened? Give me a sec. There's something wrong. No, that was okay. Sorry about that. So let's start with what the state of the art in seismic modeling is. Here is a very simple masonry structure tested in Portugal in University of Minho. It is just 3 walls, nothing complicated. And the avant-garde of masonry researchers shook it on a shake table with increasing ground motion intensity and invited 17 experts to predict the peak ground acceleration that caused collapse. They use all different kinds of methods, models based on rigid body dynamics, finite element models, discrete element models, and this is what they got. Okay, the experimental peak ground acceleration was 1.27 g, and the world experts predicted from 0.25 to 1 g. All these are stellar researchers, and for sure they know much more than me on masonry. Now, who would you believe if it would have been for a real structure? If you were the checker checking their design. If you ask them to vote, still you're getting almost 1/2 of the overturning PGA, peak ground acceleration. There is no way to know a priori who's right and who's wrong. I mean, you read blind prediction contest reports, and usually it is not that you can find something wrong. The sad truth, so, is that we have no clue how this simple structure behaves. Many people are very proud of their fancy numerical model and do not really want to admit this hard truth, but this does not make it less of a truth. After decades of earthquake engineering, we cannot predict the response, not even of this simplistic specimen. Reinforced concrete results are not much better. Here are the results of a blind prediction contest on some tests they did in UCSD in San Diego in 2006. They built a 7-story slice of a reinforced concrete building. They shook it and invited experts to predict the response. Measured displacement was around 40 centimeters on the top, and the experts predicted between 12 and 60 centimeters. To avoid misunderstandings, I'm not blaming the experts here. It is not their fault. I would probably have done worse. The thing is that this is as much as the scientific community knows about the seismic response of a structure. So what will we say to my dad who graduated in 1964, or to any practicing engineer who will step in and say, I can do equally bad with some back of the envelope calculations? What exactly are you guys doing in the university all these years? Provocateur as I am, I will also ask one more question. Are these tests repeatable? Meaning if you shake it one more time with the same ground motion, will you get the same response? I have asked some pretty well-known people running shake tables around the world, They smiled and they told me, we don't really know. And obviously they don't. Who's going to fund you to test this huge structure twice? But understandably, if these tests are not repeatable, then these blind prediction contests are useless. There is no right answer. So let's keep the above questions open, and let's take some time to study a much simpler model and see how well we can predict its seismic response. So that's the rocking oscillator. It was first studied by Housner in 1963, and this is where I got this figure from. This is why it looks a bit old. At that time, Housner observed that after the 1960 Chilean earthquakes, some tall water tanks that seemed unstable behaved better than structures fixed to the ground. And this is when it all started about studying this sort of oscillators. Why we care about it? Because this uplift down here works as a mechanical fuse, and we can use it as a form of seismic isolation to reduce the design load of the foundation in bridge design. Because the out-of-plane behavior of masonry is essentially a rocking oscillator, because museum artifacts are closer to the rocking oscillator than to the elastic one, and because some very important nuclear waste containers, they slide and rock. Now, let's see the dynamics of a solitary rocking block under ground excitation UG. The block has a semi-diagonal R and a slenderness angle alpha. We will make the following assumptions. A, the block and the support are rigid. B, there is sufficient friction to prevent sliding. And C, the motion is planar. Under these assumptions, we take moments around this corner down here, and we get the equation of motion. You might observe that there is no constitutive law involved, apart from the assumption that everything is rigid. It is only Newton's laws. So the model should be accurate unless we're moving close to the speed of light, which we're not. By the way, I mean, I know that equations do not look very nice on PowerPoint, but you can recognize that these are the inertia forces. This is the gravity moment. And this is the seismic moment. Now, what happens during impact? Well, Housner made the following assumptions. The impact is instantaneous. And second, the impact forces are concentrated at the impact point. Based on these assumptions, one can take conservation of angular momentum around here and get that the coefficient of restitution that is post to pre-impact angular velocity is that much. 1 minus 3 over 2 sinus squared of alpha, where alpha is this. This approach cannot capture any dependence on the material, but at least it tells us that more squat blocks dissipate more energy, which is the dominant phenomenon. So I have used this kind of models for more than 10 years. Let's see if they get validated, right? So we built this very simple aluminum model that can rock out of plane in this direction. We put it on the shake table and we shook it with two ground motions, el centro and leftada. By the way, when you scale the ground motion in time, similitude dictates that this is like scaling the size of the specimen. So we applied time scaling factors to the excitation that give prototype structure heights of 5, 10, and 20 meters. And this is what we got here. The black line is the experimental tilt angle, time history. Tilt angle is this theta. The red one is the numerical one when using Housner coefficient of restitution, and the blue one is the numerical one when using an experimentally obtained coefficient of restitution. The results look really bad. Okay. The first problem is that none of the numerical model predicts the response well. For me, this was catastrophic because I have more than a dozen papers published on such analytical models. And if the models cannot adequately represent reality, no matter how many citations I get, I think the papers are no more than garbage. The second problem is that a slight change in the coefficient of restitution leads to a huge change in the response. Look at the coefficients of restitution. Housner predicted 0.9465, and experiments showed 0.9532. Remember, coefficient of restitution is post to pre-impact angular velocity. I mean, compare these two values. How much better could Housner do? But this tiny difference, and here is the problem, leads to very different solutions. This is the definition of chaos. A small perturbation leads to deviating solutions. This is what people that do not like to let structures uplift see, and they claim that rocking cannot be used as a seismic design technique. They say that not only our models are not good enough to predict the response, but the response is inherently chaotic. No model can predict the response. I would add that from their point of view, the situation is even worse. The tests are not repeatable. Here I know, I didn't ask, I did it twice and I don't get the same response. So there is no right answer to validate our models. If I launch a blind prediction contest, I will be essentially fooling the contestants. Now, if the tests on this aluminum model manufactured with Swiss accuracy are not repeatable, why would I expect that the tests on a masonry wall that rocks out of plane should be repeatable? But here, are we posing the right question? What do I mean by this? Take, for example, the buckling load of a cylindrical bar. If we ask, what is the buckling load? This is absolutely predictable. Euler found it some centuries ago. If we ask, what is the direction of buckling? This is absolutely chaotic and non-predictable. Does this mean that we will not design compression members? Or take the kinetic theory of gases here. If we ask, what is the force on the wall of the cube? This is absolutely predictable. If we ask, what is the trajectory of the molecules? This is absolutely chaotic and non-predictable. So we need to ask the right question in earthquake engineering. So what is the right question in earthquake engineering? Back in 2014, I had attended a talk by Professor de Jong. At the time he was in Cambridge, now he's in Berkeley. And I remember Professor Smith from EPFL, who had asked him, with so much uncertainty in the excitation, why do we give so much emphasis on structural modeling? So inspired by this question, we thought that we need to revisit the structural model validation procedure in earthquake engineering. The earthquake engineering design question is not find the response of a structure to a single ground motion, but find the statistics of the responses to a set of ground motions that define the seismic hazard. You do not design for one ground motion, but for an ensemble of ground motions. So for those of you that are not familiar with earthquake engineering, this problem really is of academic nature. You never design for one ground motion because you don't know the ground motion. They give you a bunch of ground motions and you're asked to find the median, the maximum, some percentile of the response, or the whole CDF of the time maxima. Hence, we claim that the validation procedure should be aligned with this question here, not with this. So the numerical model should be able to predict the CDF correctly, not the response to each ground motion individually. Now, luckily, our specimen is resilient. Okay, that means that our tests do not damage it. So you can do multiple tests. Worst case is that it topples. This is a 0.5 meter specimen. Just pick it up. You don't even need the crane. So this means that we can follow a statistical validation approach. And using the Razayan and Derkuregian model, we created two sets of 100 synthetic ground motions each that are statistically compatible with the seed ground motions of El Centro and Lefkada. Here are their elastic spectra. Then we scale them in time so that the specimen has a height of 5, 10, and 20 meters in the prototype scale. So we shook our specimen 2 ground motions, El Centro and Lefkada, times 3 scalings, times 100 different statistically compatible ground motions. This means 600 different tests. And here are the results. We plotted the numerical versus the experimental maximum response for its ensemble of 100 motions. Had the model been perfect, all the 100 dots should have been on the diagonal. Here is experimental, here is numerical. They're not on the diagonal, actually they're far away from the diagonal. There are cases where numerics predict overturn, but it barely uplifted, and the other way around. So the first impression is that Housner's model is not good. But there are some good news. The model looks non-biased. Okay. So if we plot the same data, not some other data, as a CDF, the numerical and experimental CDFs match perfectly. Why is this? Because Ian Smith was right. For this specific case, we cannot yet generalize. The ground motion uncertainty overshadows the modeling uncertainty. So we should only demand that the model be non-biased, not more accurate than it already is. Hence, this good old 1962 model is not perfect, but it is good enough for the scope of earthquake engineering, and whoever is trying to refine it most likely is wasting his or her time. Now, in the end, is rocking motion chaotic or not? The question is not philosophical or of linguistic nature. It is purely practical. In the end, we're doing all this to create a design method for bridges. Remember this uplift that I was showing before that works as a mechanical fuse. If our system is classified as chaotic, then there is no way that any Ministry of Public Works, Caltrans, DOT, or whatever authority of public works will adopt it. So I'll get into this linguistic discussion, and I will ask, what is chaos? Mathematically speaking, chaos is only defined for initial value problems, IVPs, for the problem on the left, not the one on the right. So mathematically, it makes sense to ask whether this system is chaotic, and it is, but it does not make sense mathematically to discuss about whether this system, the system of interest, is chaotic. It is like asking whether a complex number is positive or negative. It doesn't make sense. And indeed, the term chaos was coined 2,700 years ago in mythology to refer to what existed before the creation of universe. So I'm sorry, yeah, I mean, I forgot to mention here, sorry about that, that it doesn't make sense mathematically, okay, but people that accuse rocking of being chaotic, okay, do not have Lorentz definitions or Lyapunov exponents in mind. They just use the word as a fancy term of saying unpredictable. So I will relax a bit the math over here, and I will use chaos. I will try to use it in the broader sense that everyday people use it. The term chaos was coined 2,700 years ago in mythology to refer to what existed before the creation of universe, and nowadays it is used in a much broader context than the one of Lorentz. According to Oxford Dictionary, it means complete disorder and confusion. Snow caused chaos in the region. Or in natural sciences, it is used to declare unpredictability. And if you Google, you will see that a mind can be chaotic, a room can be chaotic, or a city can be chaotic. I see no initial value problems here. So why should we give away the term to the mathematicians? So in that sense, I claim that in everyday language, we are allowed to ask whether this system is chaotic. And the answer is no, it isn't, because we can accurately predict the CDF. So we prove that planar rocking is predictable up to now. But real structures are 3D, and 3D rocking is notoriously unpredictable, at least when one tries individual ground motions. So we tested one more conceptual model. Here it is. Let me switch to this so I can play. Yep. Okay. So here's the model: 4 steel columns with hollow cross sections supporting an aluminum slab. All connections are dry, but we have used these restrainers here, the black ones, shown as blue here, to constrain the columns not to roll out of their original position. We wouldn't want this for a real bridge anyways. So again, we shook it with 2 sets of 100 synthetic ground motions each. The synthetic motions were created now based on 2 seed ground motions, one from the El Centro again, and one from the Chichi earthquake. The objectives of the tests were to answer 2 simple and fundamental questions. Are the tests repeatable in the statistical sense? And B, are the results predictable with numerical models? To answer the question of repeatability, we divided the sets of ground motions to subsets of 50 ground motions each. We plotted the CDFs, and we performed the Kolmogorov-Smirnov test of statistical fit to see whether the CDFs match. So we got some pretty high p-values over here. But since the results would depend on the subsets we chose, we repeated the test with 100,000 random samples, and we got a mean p-value of around 0.5, showing that the CDFs match well. Anything above 0.1 would do. So the tests are repeatable in the statistical sense. To answer the question of predictability, together with colleagues from Berkeley and the Pacific Earthquake Engineering Research Institute, we co-organized the 2019 Peer Blind Prediction Contest. For the first time, the contestants were asked to predict CDFs, not results to individual ground motions. 13 teams participated. They used finite element, discrete element, and analytical dynamics models. Here are the results. The black line is the experimental CDF. Some contestants indeed predicted the response well consistently in both cases. The best model was the one from the group of Professor Christopoulos from the University of Toronto that used finite elements. That was team 9, the dashed orange line. And the second best was the one from the group of Professor De Jong from Berkeley that used discrete element models, and that is team 3, this line here. Now, some interesting observations. Both finite element and discrete element models can predict well, can perform well or poorly, depending on the parameters used. There is no basis to recommend finite element against discrete element or the vice versa to model 3D rocking structures. The models that performed the best used zero or extremely low Rayleigh damping. However, they did include an energy dissipation mechanism. They explicitly modeled friction. This shows that damping should be modeled with methods that make sense physically. Rayleigh damping doesn't. So from our work on rocking structures, we concluded that A, models that could not predict the response of a simple structure to a single ground motion were good enough to predict the response to sets of ground motions. And B, tests were not repeatable under individual ground motions, but were repeatable in the statistical sense. Now, the obvious question is, can we do the same thing and hide our lack of accuracy under the carpet for more realistic structures like the ones that I initially discussed, the blind prediction contest ones? Well, the main issue is that our toy model does not get damaged. When it overturns, you pick it up and you test it again. This is not the same for a more realistic full-scale specimen. So for 100 ground motions, we would need 100 virgin specimens. Now, E-Defense in Japan, which is the largest shake table in the globe, charges around 2 million to test a 4-story building at full scale, just for one test. And we won't say 100. So this will not work at full scale. Actually, at full scale, it is already a huge thing to do simply one test, not 100 tests. You see San Diego, the prices are okay, a bit cheaper, but the shake table is not that large. Anyways, this shows, I mean, that doing multiple tests at full scale is out of the question. So what people do, they try to do shake table tests at a reduced scale. Now, when you reduce the scale of your specimen, you call the full scale thing that you would like to have tested, but you don't have the money, the prototype structure, and you call the small thing the model structure. So you test this. Assuming that they're made of the same material, when you scale down n times, the eigenperiod decreases by n times, and the stresses within also decrease by n times. So you have some phenomena here that are size dependent. For the sake of the discussion, I mean, I'm sure that you have seen this before in elementary physics. Actually, I picked this up from a book on high school physics. The fact that when you scale down something, the stresses decrease is something that nature has adapted to. Now, here is an elephant, and you see how big the legs are in proportion to his body. And here is an ant, and you see how thinner the legs are in proportion to the body. Now, if you try to take the ant and scale it up to the size of an elephant, this is intuitively, you understand that it's going to collapse under its own weight. It doesn't work. So what do people do when they reduce the scale of the specimen? You need to preserve similitude. And to preserve similitude, you write down your response as a function of the parameters that govern it. So this is the displacement response, and it is a function of a characteristic length of the structure. Assuming that you have a linear material, the stress-strain material law. Actually, this holds not only if it's linear, even for non-linear, but assuming that you have a law that can take this form, a material law that can take this form. It is a function of the material density, which doesn't change when you scale down. Neither this changes when you scale it down if you use the same material, or we pretend it doesn't change because For concrete, for example, it does change. This is the gravity acceleration, this is the ground motion, and this is time. Applying Buckingham's theorem, in order for the small and the big thing, to be similar, you need all these three terms in the model and prototype scale to be the same. So how can I preserve these terms, preserve similitude when I scale down? The standard thing that they do in structural engineering is called artificial mass simulation. So this G is constant. You reduce the length, so you also need to reduce the time scale, so you move everything faster at a higher frequency. This G is constant, then U of G should also be constant, the acceleration should be constant, but you need to scale in time your ground motion. For this term to stay the same, if G is constant, then L is smaller, rho is a property of the material. This does change, but it doesn't change a lot when you scale down. So what do? The idea that they do, especially for concrete structures, is they put extra masses on each floor. This is what's called artificial mass simulation, so that this term more or less stays the same. Like apart from the equations, you want your stress down here to be the same with the stress down here. Okay, and the way to do this is you add extra masses here. Now, there are limitations in this approach. Reinforced concrete and masonry properties are scale dependent. So when you scale down, you assume that the load doesn't change, but we know that a smaller specimen of concrete has a larger strength for reasons that are well understood. The second problem is that it alters the distribution of masses. Okay, so you had a given distribution and now more masses here. Now for reinforced concrete structures, that's not a big deal because all the mass was concentrated at the slabs anyways. So this is not a big deal, but for masonry, this is a problem because you cannot increase the mass of the walls. And the second problem is that there is a limit in scale for practical reasons. If you start scaling a lot, you need so much mass that there is no space to put it. That's one thing when you go to very small scales. And the second is you cannot really manufacture the small specimens. Like if you go, for example, to 1:30 or 1:40, this is reinforced concrete, the aggregate becomes sand. Okay, you can solve this, but the rebars become wire. So it's not really easy to manufacture. Anyways, this is what the structural engineers do. The geotechs do something else. They have been using this the so-called geotechnical centrifuge. So this thing starts rotating, and this is a hinge, and as you rotate, this starts rotating upwards on its own, okay, under the centrifugal force, and this creates an artificial gravity here. Okay, this way they manage to increase G. So L is smaller, but G becomes larger. So then you don't need to change sigma or rho, as long as you create a G which is proportion to 1 over L. Okay, so this is a geotechnical centrifuge, and you can go to G's up to, for example, in the ETH, the one that they built now, they can go up to 250 G's. Compare with Jupiter has a 2.53 G gravity acceleration, and the Sun has around 28. Centrifuge testing is not new. It was invented in the 30s by the geotechs. It went sort of in parallel in the Soviet Union and the US. The main difference is that in Soviet Union, they believed more in geotechnical, in centrifuge testing. In the US, the dominant figure at the time of soil mechanics was Karl Terzaki, who didn't really like it, but he was wrong, according to Cambridge professor Andrew Schofield. This is what he wrote in a paper in 1998. Now, centrifuge testing, and why don't structural engineers use it? Again, as I said, because concrete and masonry properties are scale dependent. For concrete, the larger the specimen of the same mix, the smaller the strength. Masonry, how the properties scale with size, go figure. I mean, there are a bunch of papers over there, but it's even more complicated. And the second reason is that you cannot manufacture the specimens. Aggregate becomes sands, as I said, rebars become wires, and masonry becomes like a Lego. But if we want to do multiple tests, going at the very small scales might be the only viable option. Remember, it's not a good to have thing. I mean, if the tests are not repeatable, you need to do many of them. So let's examine the blind prediction contests once more. So in order to understand where the error comes from, let's try to break the problem down to different levels. So you have the material level, that is in the case of reinforced concrete, the behavior of concrete and steel. The relevant question is, given the composition of concrete, find the compressive strength. The models are not perfect, but are far better than what we saw in the previous slide. Plus, one does take specimens from each batch and test them. Then when we go to component level cyclic behavior, for example, like you have this column, and you grab it and you go back and forth. Okay, this is cyclic loading of the column. Numerical models make several assumptions to go from material to component level behavior, beam theory, fiber or lumped plasticity elements, rebar, bond, etc. Blind prediction contests at the component level here are not that bad. So our models up to here, they do not perform that bad. So then we make some more assumptions related to interaction of components, formulation of damping, etc., to go to system level behavior. And we have the mess that I showed in the previous slide, not in the previous, in one of the first ones. Okay, so schematically, here it is, material level, assumptions, component level, more assumptions, system level. Here is the weak link, because here we're doing well, here is where the mess is. The weak link, what I call the global level assumptions, is damping formulation, Raleigh, non-Raleigh, something else, component interaction, and boundary conditions. It is not a surprise that our models do not perform well at this level, because we have very few experimental data points to calibrate them. Now, imagine if these assumptions only work in the statistical sense, then going small scale is not a good idea to give you an ERC, but a necessity. There is no other economically viable way. So our idea is to focus only on the global level assumptions, only here, for a given and experimentally obtained component level behavior at a small scale. So we will try to do small scale testing, knowing that we will distort the specimen because of the scale dependence of the material properties, but we will quantify this dependence by doing component level testing, and then just focus on calibration of our models, of calibration of our global level assumptions that the models do. So how do we go at such a small scale? See, here is what the geotechs are doing for reinforced concrete. There are several problems with this. This is good enough for the geotechs. We're mainly focusing on soil. This is supposed to be a column. But the first issue is the accuracy. I mean, really, this doesn't really look nice. I think you cannot see my laser pointer. Let me see. Let me fix it.
We can now.
You can. You cannot, or you can?
Yeah, we can. I can see it.
You can see it. Okay.
Yeah. Your mouse. Yeah.
Okay. So this is what the geotechs are doing. I mean, this looks bad. Okay. That's one thing. The second thing, it took 8 hours of a poor PhD student or a postdoc, I don't remember, trying to do this by hand, just for one column. And you cannot do the joints. I mean, if you have a column and then a beam, and I mean, this cannot be done by hand. So our idea is to use a 3D printer to manufacture the specimens. Here are some cages that that we built using a metallic 3D printer. This is supposed to be the reinforcement of a column, and it has the size of my finger. This is 6 centimeters. Now, the good thing with the 3D printer is that you can go to very small diameters. So here is a photo of the rebar. The rebar has a diameter of 0.5 millimeters. Okay, and you can also print the 0.05 millimeter ribs. By no means you cannot do this. You can do this with anything else than a 3D printer. Now, we tested these rebars in tension. Some results that we got, but we have already fixed this, but I do not have the formal results yet. Here is the stress-strain relation of the rebar, of the material of the rebar. You see that there is some pretty large dispersion over here. I mean, the strength of the 3D printed steel is close to what you would be expecting for rebars, but the dispersion is larger. Okay, and for standard rebars, you would expect this dispersion to be smaller. But I think this has to do with the size of the sand, of the powder, of the steel powder that we were using. We need to use a smaller one because this essentially reflects imperfections over here, which we need to reduce. So these were some tensile tests. And then we tried to do the standard test that they do for a column. We built a small scale column. Again, this is the size of my finger. These are the rebars. And we grab it from here and we went up and down, which is a standard test that they do for reinforced concrete columns. And then we tried to fit an OpenSys numerical model to the results. And the results, okay, they could be improved, which we're currently working on, but they're not far away from reality. So we have managed to have a small scale specimen which follows the same, which can be modeled by using the same models that we use for full-scale specimens. Okay, maybe you need to calibrate a bit some parameters, but conceptually it is the same model. Now, when you go to masonry, and this is where the term metamaterial might fit. The key challenge is to print material with similar properties to masonry. Now, masonry, unfortunately, comprises two materials, the bricks and the mortar, with mortar being the weak link. Okay, as far as I know, there are no 3D printers, sand-based 3D printers or 3D printers that could print brittle materials using two different materials. So we can only use one material, the material that is printed with our 3D printer, to emulate something that comprises two materials. And the way to the solution we found to this problem was to emulate mortar, which is the weak part, by printing notches and shear keys. To get funded, you call this a metamaterial, a metamortar. Okay. So this project has been a bit delayed by COVID, and we're currently at material characterization. Before I go there, let me explain you a bit how this 3D printer works. So you have this thing over here called a recoater that, first of all, you have a box, okay? And this recoater passes and lays a very thin layer of sand. Then after the recoater lays the sand, you have this guy here, which is the print head, that essentially sprays some glue. And it sprays this wherever it needs to be sprayed so that you form a cross-section of what you want to print. And this works, as you can guess, with strips. So it glues here whenever it needs to glue, then it goes like this, and then like this, and so on. So in the end, you expect an orthotropic but anisotropic material because it is printed by layers and by strips. So we're at the point of performing tests at the material level. And we see that there is some orthotropy in compression. So this is the compressive strength in X, Y, and Z direction, but not something that that creates a totally different material in 3 directions. This is X, Y, and Z. You can also see that there is no scale effect, at least for the cubes we tested. We tested 50, 75, and 100 millimeters cubes, and the strength was similar. Similar results you can observe about the bending strength. But obviously what we want in the end is to have some walls. Now here is a full scale real wall tested not by us, by the group of Dr. Vassiliou. So you apply a compressive load up here. You make sure that this does not rotate. The top cross section does not rotate. So you have 2 actuators. And then you grab it from here and you go back and forth. And this is the failure pattern that they observed, a crack propagating through the what we call in masonry head joints, through mortar. We managed to do the same thing by using this 3D printed physical model. Actually, this is from some years ago. Now after characterizing the material, we're ready to perform more tests. And apart from a qualitative match, try to also have a quantitative match. So don't get me wrong, I know the limitations of the whole thing. The printed material, the printed model is not necessarily a physical model of a prototype. We will use it only for the validation of the assumptions that we make to scale up from cyclic component to dynamic system level response of the weak link here. We're not claiming that what we print is a true replica of the full thing. So by studying 3D printed models, we cannot predict the response of the prototype material. We cannot predict the response of the prototype component. For the above, we need to test prototype material and prototype components, the full scale thing, but these are relatively cheap at the component level. You can do them. We seek to answer questions like, what kind of model should we use? Because we don't even have answers. We don't have answers not even to these questions. Finite element, discrete element. Are simplified methods often used in practice, and especially in Switzerland, enough in the statistical sense? What should be the formulation of damping, not the value? Raleigh, initial stiffness proportional, tangent stiffness proportional, second stiffness proportional, something else. These questions, you have giants of earthquake engineering disagreeing with each other. You have Chopra having a different opinion than Fardis, having a different opinion than John Hall, having a different opinion than Miranda. So you have Berkeley versus Caltech versus Stanford versus University of Patras. 3 out of 4 of these people are the editors of the most important earthquake engineering journal. Now, and another question is, does the excitation uncertainty overshadow the uncertainty of the structural model? So these are the limitations, and I'm not claiming that we can do everything with this. So the conclusions of the second part is that we can use a 3D printer to manufacture the reinforcement for 1 to 40 reinforced concrete specimens. There is a concrete missing here. And that we're working on using a 3D printer to emulate masonry. I think this is it, and thank you for your attention.
Excellent talk. Thank you so much. I'm sure there will be lots of questions. I have thousands of questions, actually. I understand that you don't like the word, perhaps, metamaterials, but I can see some mechanical metamaterials in there, you know, and so on. I mean, all this.
It's not that I don't like the term. I don't like the fact that you need to use some fancy terms to get funded. The term has nothing wrong.
But no, I agree with you. That's the rule of the game, that nowadays, if there is no sexy term, let's say.
Yes.
Yeah. Okay, that's fantastic. So do we have any question regarding the Buckingham theorem, regarding, you know, shaking things? Yeah, Martin, please do.